Hello, everybody. This is the tutorial for how to calculate the number of sulfhydryl groups or the number of cysteine residues um, in the iodoacetate reactions. So just to kind of like get everyone situated, this is the flow chart and also recipe figure 9-6 from your lab manual. And essentially, just to remind everybody, you set up two reactions: a negative control reaction where you had no protein whatsoever, no GAPDH enzyme in reaction number one. And then here, I think everyone should have calculated about 26 microliters of the GAPDH stock that we had given you based off of this fold X strength factor and also the final volume of that reaction. Once everybody pretty much had set up their reactions, you were then asked to take out 20 microliters for dye binding assay. So in the second half of this tutorial, we will be calculating also how to properly calculate the amount of in terms of mass of GAPDH that was in your iodoacetate reaction based off of your standard curve data, and then also relating that to the number of sulfhydryl groups or the number of cysteine residues in the reaction that was picked up by the iodoacetate labeling. From there, you were left with 45 microliters of this reaction because 20 of it was taken for dye binding assay, and you can't use that anymore. And then of the 45 microliters that you were left with in each tube, 5 microliters of the C-14 iodoacetate was spiked in there for a final reaction volume of 50 microliters, which you allowed to sit at room temperature for 1 hour. You diluted it by adding 10 microliters of 6 millimolar DDT. And then from there, you only used 50 microliters of this 60 microliter stopped reaction at this point, and then diluted it further tenfold and used a tenth of that for your spotting and your TCA precipitation from the original, or I should say from the diluted 500 microliters that you had here. Only a tenth of that reaction was used to make 3 TCA precipitation reactions and 3 direct spots. So I have the sample calculation to kind of help you basically move and progress forward with the calculation, starting with your 3 individual plus GAPDH filtered CPM values and minus GAPDH filtered CPM values. So these were the 2 reactions that I was talking about. For this specific calculation, you will not be using any of the direct spots. So we don't use those 6 plus GAPDH direct spots and 6 minus, or sorry, I should correct myself. You're not going to use any of the 3 plus GAPDH direct spots, nor the 3 minus GAPDH direct spots. This is all the filtered CPM values for the plus GAPDH, so that's your experiment, and the minus GAPDH. Not only is it your negative control that we're treating this at, but we also want to subtract out the background CPMs so that we can actually get a corrected CPM. So the first thing that we need to do is average our 3 plus GAPDH filtered CPM values and also average our 3 minus GAPDH filtered CPM values. I've already did the math here, and I'm also for these calculations, I'm showing you what the what my calculator would basically show you, but then in the second more refined answer, I'm actually practicing significant figures here. That being said, for these 3 or sorry, I should say these 6 data points, I'm practicing 3 significant figures because those are the data that I acquired here in this set. Yours might be a little bit different, especially if your plus GAPDH filters are going to be in the thousands or so. So using proper error propagation procedures, I would add these three sequentially using my error propagation addition formula, and then finally divide by 3 to get my average plus GAPDH CPM values and my average minus GAPDH CPM values. So from here, once you have these two CPM values, you want to correct your experimental CPM values for the background CPM values. So the way that you're going to do this is essentially you're going to take your plus GAPDH, your average plus GAPDH CPM values from the previous step, and then subtract out the negative control or the background minus GAPDH CPM values, the average there that was pre-calculated before here. And what I'm left with is a corrected CPM of 556 plus or minus 2.23 CPMs, which I've rounded down to plus or minus 2 CPMs to be in accordance with significant figures here. This is basically telling me the amount of radioactive CPM that's coming from my experiment, because it's assumed that I would also have this same amount of background reading also present in my experiment as well. But I can, because I did the background alone reaction, I'm able to subtract that out. All right, great. So we have our corrected CPM values for our experiment. Now it's time to do a good amount of conversions. And this is kind of where we would probably end up losing about a good majority of the students here, just because there's a lot of conversions that aren't taken into account, but at the same time, it's not really, apparent from the procedures why you would need to take this into account. So hopefully you understand that this is from filtered CPM experiments, meaning if we go back to that flow chart of our experiment that I showed you earlier, that signal is coming from all the way down here in this flow chart. So we basically have to go back and back calculate as much as we can to any of these squares down here, to where we pretty much have the total amount of radioactivity, and also that we can connect it to a total amount of GAPDH. The total amount of radioactivity, of course, then we would convert that with more conversions to the total amount of iodoacetate, total amount of sulfhydryl groups, total amount of cysteine residues. And then we can find that ratio of how many cysteines there are per GAPDH. So the first thing that we need to consider is, after the reaction was stopped with 10 microliters of 6 millimolar DTT, only 50 microliters out of the 60 total was taken to the next step for dilution and TCA precipitation. So I'm talking about this step right here. Only 50 out of the 60 was removed to then use for dilution and then TCA precipitation, and so on and so forth. So what we have to do is, knowing that, we need to incorporate a 5/6 correction factor, because we only took 50 out of 60 microliters to make the TCA precipitation. Then the sample was diluted to 500 microliters. Now, this dilution step actually really doesn't matter too much. Any kind of dilution afterwards doesn't really matter. So as long as you continue to use all the material. Oops, made a boo-boo here somewhere. Okay. But the part that we need to take into account is only when we are then measuring for filtration a small portion of the dilution. So for example, each of these filters, these filtrations, we're not like losing any material. Yeah, we are diluting it with more BSA and some TCA, but basically that entire TCA precipitation was then applied to the filter apparatus completely. And so the only thing now that we need to account for is that this filter here was only 50 microliters of what was originally a 500 microliter diluted sample. And so then that's our other conversion factor that we need to take into account when we're doing our back calculations. Thus, we need to take into consideration a 1 to 10 correction factor, because these TCA precipitations are only a tenth of this 500 microliter dilution. So we'll take our previous answer of our corrected CPM. In my case, for the sample calculation, it's 556 plus or minus 2 CPMs. And then now we're going to undo all of these, what do we call this? These, reduction in signal by basically either dividing by the fraction itself or multiplying by the inverse, the reciprocal of these fractions, I should say. So I'm going to multiply by 6/5 to undo this 5/6 factor that was applied to during the experiment. And then also I'm going to multiply by 10/1 to undo this 1/10 sample that was applied to close to the TCA precipitation procedure. And when I do that, my CPM values increase significantly. They go from 556 plus or minus 2 CPMs all the way to what will then be rounded down to 6,670 plus or minus 20 CPMs. So this is a very minor back calculation step that has to be accounted for. Otherwise, your final values will be very, very low and very off. All right, so this is kind of where now we just basically have to do some conversions to go from CPMs to DPMs, DPMs to radioactivity, and then radioactivity to total moles of sulfhydryl groups or cysteine residues. So the next step is, once we have our corrected and back calculated CPMs, we will then convert that to disintegrations per minute or DPMs. So CPMs is a result of the disintegrations per minute value, radioactive amount that is intrinsic to the material. CPM is what the detector is actually measuring in the scintillation counter, and that is based off of the scintillation counter's efficiency. So even though the scintillation counter told you how many counts per minute it was observing per sample, that is related to what is actually being emitted from the sample itself. And we know, and we can calculate this efficiency by basically calibrating the scintillation counter with known standards of C-14 containing vials. If we can calculate how many disintegrations per minute there should have been in there, and the efficiency was the scintillation counter is 100%, then basically disintegrations per minute will equal counts per minute. But that is never the case. We always need to calculate this efficiency. And for this semester, the efficiency of the scintillation counter is 96.87%. So we have to convert that as a decimal, which is 0.9687. And then we set up our equation so that we put our back calculated and also corrected CPMs here on the left side of this equation. We'll insert this efficiency in as a decimal form, and then solve for DPM. So disintegrations per minute equals 6,670 plus or minus 20 CPMs divided by 0.9687, which will then give me a calculated answer. And then I will round that off to then acquire 6,890 plus or minus 20 disintegrations per minute. Now that I have disintegrations per minute, I'm able to relate that to how much radioactivity I have in terms of microcuries. And the relationship between disintegrations per minute and microcurie is that 2.22 times 10 to the 6 disintegrations per minute equals 1 microcurie of radioactivity. So I'll take my previous answer in disintegrations per minute and then multiply by this conversion factor here having 1 microcurie at the top, 2.22 times 10 to the 6 disintegrations per minute in the denominator. And then I am essentially here, I have this answer, this calculated answer in scientific notation, which I then, round it off to 3.01 plus or minus 0.01 times 10 to the 3, negative 3, sorry, microcuries. And of course, you can, if you want to, convert, if you don't want to put your answer or kind of deal with scientific notation at this point, you could, of course, convert this to nanocuries. But I would recommend for this step, just keep it at microcuries, because the next conversion that we have is relating the microcuries of radioactivity to the actual micromoles of the reagent that we essentially have in the reaction of the test tube. So because this is given in microcuries, I would just kind of strongly suggest to just leave this previous answer into microcuries and just deal with the scientific notation for now. This relationship is telling us the amount of radioactivity that we are observing is equal to some known amount of reagent that is actually present in the assay itself. So this ratio of how many, what we actually can see and detect in the experiment, relating it to what is actually how much of that is actually present in terms of like total radioactive and non-radioactive iodoacetate. Because just to give you a little bit of appreciation for the experiment, we don't just have hot radioactive iodoacetate that we have given you. It is a mixture of hot radioactive iodoacetate and cold non-radioactive iodoacetate, because otherwise our CPM values will be very, very high. And also we don't, if we don't have to deal with as much radioactivity as we need to, we're not going to. One of the basic principles of working with radioactivity is the acronym ALARA, which stands for as reasonably or as low as reasonably achievable. And so if there's a way that we can do this experiment without having to use as much radioactivity than just, pure radioactive iodoacetate, then of course we'll go ahead and do that. That relationship between the radioactivity that we're detecting and the actual amount of iodoacetate, radioactive and non-radioactive, in there is 2 microcuries equals 1 micromole. So we will take our previous answer after we've converted DPMs to microcuries, and then we'll multiply that by the correction factor of 1 micromole of iodoacetate is equal to 2 microcuries of radioactive iodoacetate. And so now we're going to go from microcuries to micromoles. And this is where I've left the calculated answer in scientific notation, 1.505 plus or minus 0.005 times 10 to the minus 3 micromoles, which I then did 2 steps here. I rounded it to be complete with 3 significant figures, or sorry, in accordance with 3 significant figures. And I also then converted micromoles to nanomoles by removing the 10 to the minus 3 there. So this here is the answer that you, or 1/2 of the answer that you are going to get for these conversions, is the nanomoles of cysteine residues, or the nanomoles of sulfhydryl groups that you end up detecting or measuring quantitatively in these experiments. So that is 1/2 of the work. The other part of the work that's part of another prompt in your post-lab write-up is actually solving for the moles of GAPDH in the iodoacetate labeling reaction. This one's a little bit more straightforward. You don't need to worry about too many conversions here. You just have to kind of understand where everything is coming from. So let's say that your standard curve data gives you a mass of your sample for the dye binding for the plus GAPDH reaction of 13.5 plus or minus 0.2 micrograms, and that's coming from a 15 microliter protein sample solution. So of course we do the division, dividing our micrograms by microliters, and then we get the concentration of GAPDH protein in our iodoacetate sample, which ends up being 0.900 plus or minus 0.013 micrograms per microliter. So that sample came from these 20 microliters right here. And the concentration in this sample in these 20 microliters here is also the same concentration of these 45 microliters here. Now, like, understand that I'm talking about concentration here. So if you have a homogeneous solution, it doesn't matter how you partition it out. If you took out 20 microliters for dye binding or 30 microliters for dye binding or 40 or 50 or whatever, what you take out for dye binding and what you leave behind for your reaction should be of the same concentration. So if my dye binding assay tells me that my aliquot that I had applied to it was 0.9 plus or minus 0.013 micrograms per microliter, then of course this tube here will also have the same concentration. And with the previous how should I call this? With the previous calculation that we did with the nanomoles of cysteine residues, we were able to basically calculate how much total cysteine residues were modified up to this point here. And so all we have to do is with the concentration of GAPDH, just multiply it by 45 microliters to get the total mass of GAPDH that we have here. So we can take 45 microliters of that cocktail that essentially we can multiply by our previous concentration that we calculated. And then I'm also going to do another step in this calculation by, I know that I'm going to get micrograms of GAPDH in this calculation, but I'll take it one step further and convert those micrograms to micromoles using the formula, conversion formula, the relative mass of GAPDH being 36,000 plus or minus 100. I know in the discussion slides, I told you to use it for grams per mole, but that's the exact same thing as milligrams per millimole or micrograms per micromole. I know that I'm going to produce micrograms here as a unit, so I'll just go ahead and put in micrograms per micromole here, so that I'm expecting a micromole answer over here on the right side. And of course, here's the calculated answer that I would just basically copy down all the digits for completeness. But then I'm doing two steps here on the next part. One step is that I'm rounding down to be in accordance with significant figures. And also in the same time, I'm converting micromoles to nanomoles of GAPDH. So once we know what our nanomoles or GAPDH is in our iodoacetate reaction, and we know how many nanomoles of cysteines we detected, now we can set up this ratio of the moles of cysteine residues over the moles of GAPDH, which essentially I would then have to use the division error propagation formula to do this. But we can kind of just basically see here, just by eyeballing this, it's going to be, the measured value is going to be 1.51 divided by 1.13, which for this sample calculation here, using this detection method, it seems that I'm picking up about 1 cysteine residue per GAPDH. You know, this will be different than your DTMB reactions, and this is definitely a great talking point in your conclusion section to talk about the accuracy of these two different methods, as well as the precision. So basically, like, you know, how large are the errors associated with those two different methods? All right. Thanks, everyone.